Hey Ramblers, this video covers chapter 9.6 in our textbook and deals with what are called Pythagorean triples or families of right triangles. Even though Pythagoras got his name attached to the theorem that a squared plus b squared equals c squared, I've mentioned before he didn't discover it. We know from archaeological finds that the Babylonians were aware of it through a tablet that was recovered called Plimpton 322. Plimpton 322 has been carbon dated as over 1,000 years older than Pythagoras, and on it is listed several solutions to the Pythagorean theorem that are all integers. So we know that this idea has been around long before Pythagoras. Nevertheless, Pythagoras was his whole school of thought centered around the idea that numbers were the essence of nature and the essence of the universe. And so they were fascinated by numbers and their relationships with each other. For instance, the number 1 represented maleness. The number 2 represented female because it could be divided evenly and made into more numbers. And it went on. And each number had a certain significance. So they were fascinated by triangles who would have sides that were integers, because they were looking for the key to the universe, and in their philosophy, something like the 3, 4, 5 triangle would certainly have held a special place, seeing that they were three small integers and consecutive integers. So formulas were developed by the Pythagoreans for finding other triples, and these formulas were also created by thinkers like Plato and mathematicians throughout the centuries. But today we're going to introduce you to a couple of Pythagorean triples, and there's an infinite number of them. But these are going to be ones that show up in our book, in other books, and standardized tests quite frequently. And I want you to memorize them. So memorize these. Take them down your notes, memorize them, and I think you'll find that they help you do the homework much quicker, and they'll help you to solve problems both in this class and in future classes. So we're also going to cover after that something called the principle of the reduced triangle. All of this is based on this idea of similarity and how the same ratios between numbers exist from one triangle to the next. Okay, this has been a long introduction, so let's get on with the material. But please take careful notes, pause the video when you need to, go back and make sure you understand the concepts. Don't just watch the video just to get it done. And we'll have some exercises to help you with this practice. Okay, thanks for watching. Families of right triangles are really prominent in this textbook and on the standardized tests that you'll take throughout high school. And they are based upon the principle that these are just solutions to right triangles that are integers. There's an infinite number of them, but maybe the most common and most attractive is the 3, 4, 5 family. The 3, 4, 5 triangle is the only right triangle whose sides are integral solutions, and consecutive integral solutions, I should say, to the Pythagorean theorem. There is an infinite number of right triangles whose sides are all whole numbers, but only the 3, 4, 5 are they consecutive whole numbers. So let's take a look at some of the other members of this 3, 4, 5 family. Well, the first would be the 6, 8, 12. There, the sides are just 2 times 3, 2 times 4, and 2 times 5. So this would be another member of the same family. Keep in mind, with these families, the largest of the family, or the largest of the triple, is always going to be the hypotenuse. The fact that all these are related is based on the similarity that we studied back in chapter 8. You should notice this familiar picture where we have a side that is parallel to a third side of a triangle, and so it makes sense that the ratio of 6 to 9 would be the same as 8 to 12, would be the same as 10 to 15. So by side, 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 all of the triangles within a family are similar. So also in the 3, 4, 5 family would be the 9, 12, 15. And we would also find the 12, 16, 20 triangle. I could go on all day. I could say that the 30, 40, 50 triangle is also a member of this family. But the point is, let's just learn to memorize the ones that come up a lot. Just to illustrate the point a little further, allow me to show you another family, the 5, 12, 13. And the 5, 12, 13 family, of course, there would be many, in fact an infinite number of members. Can you name another member of this family? Well, I hope you guessed at least the 10, 24, 26 family, which would be 2 times 5, 2 times 12, and 2 times 13. Other members would include 5 times 5, 5 times 12, and 5 times 13. Any number that's a multiple of 5, a multiple in the same multiple of 12, and the same multiple of 13 will create a right triangle that satisfies the Pythagorean theorem, and so is a member of this family. Okay, so let's take a look at all of the different families that I'd like you to memorize, simply to help you do your homework faster, and because they come up so much in this book and on standardized tests. The 3, 4, 5 family, it'll be worth memorizing the 3, 4, 5 times 2, times 3, and times 4. 5, 12, 13, 7, 24, 25, and 8, 15, 17, we will also see members of those families. So memorize those out times 2. Finally, the 9, 40, 41, 11, 60, 61, 12, 35, 37, and 20, 21, 29 are worth memorizing because they're just going to come up so often. So please take this chart down in your notes and start to commit it to memory. I think you find as you do the homework in this book, you'll recognize that these families are the solutions to most of the problems that we're going to come across. There's one more application of similarity to right triangles called the principle of the reduced triangle, and I want to take a look at that next. Okay, the principle of the reduced triangle has to do with triangles where the solutions are not all integers. So let's take a look at this example here. When you see a right triangle, as this definitely is, because there's a right triangle down here at C, and you want to solve it to get the hypotenuse or any other side, if you can recognize a common factor. So what common factor exists between 22 and 77? Well, hopefully you recognize that 11 is a common factor between both 22 and 77. So I'm going to create a reduced triangle by dividing the sides 22 and 77 by that common factor. And when I do, I get a smaller triangle. That is also a right triangle, and the sides of it are 2 and 7. The advantage of 2 and 7 are that I can solve that in my head, because 2 squared plus 7 squared is equal to 53. So I know that this hypotenuse, AB, would be the square root of 53. Now I'm going to take that and bring it back to my original triangle by multiplying the solution, square root of 53, times 11. Since I had divided by 11, now I'll multiply by 11. So I can find my original hypotenuse, AB, is equal to 11 times the square root of 53. That's a lot easier and less awkward than working with 22 squared and 77 squared. So we reduce it to a smaller triangle, solve the smaller triangle, and then multiply our answer by the same factor that we reduced it by. Okay, that's a little complicated. You'll get plenty of practice with this in the homework, but it's all based on similarity and the fact that that scale factor between triangles is going to apply to all sides. Okay, let's take a look at a couple more examples, and then we'll conclude the video. One of the best examples of a Pythagorean triple problem that we've already done is number 15 from section 9.4. You may recall that in this problem they told us that BD was 16, BC was 7, and FD was 24. Since BD is 16 and BC is 7, I know that CD is 9. And since E is a midpoint, I know that ED is 12. So, by Pythagorean triples, I can recognize this right triangle as a 3, 4, 5 triangle, where 9 is 3 times 3, 12 is 3 times 4, so EC is going to be 3 times 5, or 15. I know that since FD is 24, and this is a rectangle, that AB must also be 24. So, by using the Pythagorean theorem, or my Pythagorean triples, I know that AB is 24, BC is 7, so, by the triples, since this is another family, AC is 25. Finally, FE is also 12. AF has to be 16, since it's the opposite side of a rectangle. So I have another triple here. 12 is 4 times 3, 16 is 4 times 4, so AE is going to be 4 times 5, or 20. So, if you add up the perimeters, you get 20 plus 15 plus 25. That gives us the 60 that is there. As you can see, these triples are really handy, and they help you to get through the problems without having to use the Pythagorean theorem calculation each time. All right, let's also take a look at a quick principle of the reduced triangle problem. Suppose I was given a right triangle with sides of 9 and 27. Now, doing that in my head, 9 times 9 is 81, but who knows what 27 times 27 is? So using the Pythagorean theorem in our head would be difficult. So let's try reducing this triangle by a common factor. What's the largest common factor between 9 and 27? Well, hopefully you recognize it. It's 9. So if I were to divide my large triangle sides by 9, I'd have a triangle where one side is 1 and the other side is 3. Can you solve that Pythagorean theorem? Pause the video and try. Hopefully you found that the side of my new triangle, or the hypotenuse of my new triangle, is going to be the square root of 10. So now I'm going to use that and bring it back to my original triangle by multiplying by 9. So my hypotenuse will be 9 times the square root of 10. And that's how the principle of the reduced triangle works. Thanks for watching, Ramblers.